to 1-8, which is displacement profile problems, and I'm going to try to make it so that we can sort of see what's going on here, although it's really not getting done, so I hope you have good eyesight and can see here. So we've got 4 students participate in a 1,000 meter race. The displacement profiles are shown below. So we've got A, which seems to go with a constant slope here. We've got D, which goes in sort of a parabolic situation. We've got B, which does one constant slope and then another constant slope. And then we got C, which is doing nothing, 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 and then all of a sudden takes off and goes in a constant slope. So we have to remember what slope is on a displacement time graph. And slope equals velocity. So we're dealing with a big velocity, a very fast velocity, and then evening out and then kind of stops. Not much of a velocity, and then a big velocity, and then nothing doing, and then a pretty big velocity. So the question is, who won the race? If you really think about it, the race is 1,000 meters long, and the person who wins the race goes 1,000 meters in the shortest amount of time, which is going to be person A, because they got to 1,000 meters earliest on the time axis. So there you go. Who had the fastest speed at any time during the race? Well, that's the person who's got the steepest slope. And I would venture to say it looks like person D at the very beginning goes pretty steep up there. You can make the case for B, but I really think right when they take off, D has got the fastest time, or I'm sorry, the fastest speed during the race, and then kind of peters out as they go on through the race. Who slows down? That is person D. They started going off gung-ho with a very steep slope, and then they kind of evened out, and then at the end you can see they have almost no slope. You know, it's very. Let's see if I can do this. It's a very, 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 very minor slope, and it almost looks like it's zero, a slope of 0. So yeah, I'm just making the tangent line like we talked about in class today. So person D is the one that very much slowed down. Who didn't start the right of way? Well, that's the person that went 0 velocity, who had no slope to start with, and that was person C, because they started at 0 meters per second, 0 meters per second. I guess the starting pistol went off. Maybe I should move. And then finally, which student was passed by the most runners? This is a little bit difficult to really think about, but if you look at who was passed by the most runners, you're looking at, I would say, D, because they got out in front, and then A passed them, and then B passed them, and then C passed them. So I'm going to say that D is the one that got passed by most people. And then what is the same about runners A and C? Well, you might not be able to see it, but maybe I can bring it into focus for you. That's a good tracing of the slope of person A. Let's bring it over to C. Looks pretty close. Maybe not perfect, but I would say person A and person C had the same slope. And on a position time graph, that means they have the same velocity. And it's pretty, it's a generous thing to say, but I think that's what we're looking for here. So I hope that helped you out. And then we're going to go ahead and move down to the next sheet. So we got this thing. A toy car is moving along the x-axis is shown in the displacement profile below. So it starts at -4 meters, and then it seems to, and it doesn't do too much there, and then it seems to take off and move at a constant velocity. Again, this is a constant slope. And then here we have a parabola, so we're having an acceleration. So let's see what we can do with this. What is the displacement for the entire trip? Well, it starts at -4 meters, and then it ends at +4 meters. So final minus initial, that'll tell you the change in displacement. So positive 4 minus a negative 4 meters is going to give you 8 meters. So the thing went from negative 4 to positive 4. And again, it's not the what is the distance during the trip, it's what's the displacement. So all we care about with displacement is from start to finish. And if you look at where they finished at 4 meters. And they started at 4 meters, so that's what you're looking for in one fell swoop. And if you have a question about that, you have a sheet that's got a bunch of definitions, one of which is displacement. What is the average velocity for the entire trip? Well, that's a interesting question. We're going to look at the average velocity, which is total displacement over total time. So all we need to know is they went 8 meters. Over how long did it take them? 0, 1, 2, 3, 4, 5, 6, 7, 8 seconds. 8 seconds, which equals 1 meter per second. And that's average velocity. That's not instantaneous velocity. Instantaneously, here they're going 0 meters per second. Here they're going something else. And here they're going something else. And you can figure out what they're doing here by looking at the slope, which I assume we're going to be asked eventually. What is the car's instantaneous velocity to 4 seconds? Well, right there. Well, what's the slope at 4 seconds? So this line goes through 4 seconds, and the slope is constant, and it's constant, so we can actually use the slope for this whole line to tell us how fast the car was going at 4 seconds. And it's going up 1 over 1, up 1 over 1, so I would say it is going 1 meter per second. And we did that sort of in class today. You can say, well, we started at negative 4. Oh, wow, that's not even close to right. Sorry about that, guys. I'm off by my units. So we were at negative 4, and then we're up at positive 4, so we had a displacement of 8 meters. And that took a time of, it looks like, 2 seconds. Let's try that. So 8 over 2 equals 4 meters per second. I think that's a much more adequate answer for this. So the final minus initial again. So positive 4 minus a negative 4 gives you a positive 8 divided by 2 seconds, which is the time it took to make that happen. And that'll give you 4 meters per second. Finally, estimate the car's instantaneous velocity at 7.5 seconds. So 7.5 seconds, it's starting to come back down like that, so you can sort of get a guesstimate for what the slope here is if you make a couple of assumptions. And let me get a better line here. One of the advantages of having the smart software here, I can try and make us a nice long line, and at 7.5 we're pretty close to it. Dare I say it's going, I'd say, down 3 and over 1 second. So, you know, and again, it's an estimate. So 6.5, sorry, instantaneous velocity 7.5 seconds. I skipped 10. I'll come back to it. I'm doing number 11 right now. At 7.5 seconds, it looks to me like that slope is down 3 over 1. So I'm going to say negative 3 meters per second, but that's a guesstimate. You can have what you will. I wouldn't ask you to guesstimate something. I'd give you something on a quiz that you could very easily calculate. But here's the real good question that I wish I didn't skip. Number 10. What's the car's instantaneous velocity at 6.5 seconds? Well, 6.5 seconds looks to me like if I was to draw a tangent line to this thing, looks pretty flat to me. How about you? So if we're dealing with a flat line that's tangent at 6.5 seconds, now right here, what is the instantaneous velocity of something that is a flat line on a position time graph? And I hope you know the answer to that is 0 meters per second. Finally, Todd transit line 7.5, calculate a slope, and that's kind of what we did. So I hope you got about negative 3 meters per second. It's close. It's not definite, but I think that we're in the ballpark for what we're looking for here. I hope this helped, and we got another video coming up for tomorrow.